with me as I construct the image for you. The one that I'm going to be looking at is going to be number 35 on page 203 of your textbook. Okay, so as I'm piecing this together, actually feel free to pause the video and grab some paper, whether it's graph or just regular paper, and create the image with me. Okay, so as per usual, we have our x and our y axis. We do have a vertical asymptote that is located at x is equal to -1. We also have another vertical asymptote at 2. To add to that, we have a horizontal asymptote that is resting at y is equal to 2. And then finally, I will note this one in pink. We have an x-intercept at 1. And then I will draw in the rest of this for us. Okay, so the rest of our function looks something like this. It's going to actually flatten along the x-axis as it touches the x-intercept and then continues to go up. Please note that in this case, if you're kind of paying attention, even though you have a horizontal asymptote here and your function actually is cutting through it. And usually with this, in the case of asymptotes, especially with vertical, it's actually, they shouldn't cross. But with horizontal asymptotes, especially when it's closer to the origin on the axes, it's almost, I guess you could say, kind of weaker, so that the function can sometimes go through the horizontal asymptote. To kind of bring everything into perspective, though, the strength of that horizontal asymptote increases as you go to increasingly larger and larger negative numbers and increasingly larger and larger positive numbers. So in other words, as the function goes off to negative infinity or positive infinity along the x-axis, the strength of that horizontal asymptote increases and it does eventually become impenetrable. So in this case, again, our goal is to come up with what is this rational function that is generating this image that we're seeing before us. So one of the first things that I would say to do is, okay, just for the back burner, I'm going to note that the horizontal asymptote is at 2. Okay, so I'm going to set that aside. I will use it for later as I begin to assemble what this rational function will look like. So now let's go ahead and take a look at the vertical asymptote. So we have a vertical asymptote at -1. So in other words, if I were to write that as a binomial factor, this would be x plus 1. Also kind of take a look and see what is happening to the function as it approaches the asymptote from the left and from the right. So notice on the left side of this asymptote, we are seeing that the y values are going off into positive infinity. But on the right side, the y values are going off to negative infinity. In other words, as you've probably already figured out, they're going in opposite directions. So what does that mean? When does that happen? And hopefully what you're saying as well is when it has an odd degree. That's when that's happened, because you're all smart and wonderful and you know this. So in other words, we can either say that this is x plus 1 raised to the first power, or we could just say that's x plus 1. Either way is fine. Whichever way is going to give you the most clarity at this point, I would say. You will eventually want to work up to the point where you don't need to see that exponent if it is a 1. Your other x-intercept, sorry, not x-intercept, your other vertical asymptote is at positive 2. So that binomial factor is going to look like x minus 2. So again, let's take a look and see what's happening. On the left side, it goes off to positive infinity, the y values do. And on the right side, the y values go off into positive infinity. So essentially we've kind of said that this means that they sync up or that they start to mirror one another. So in this case, they're even. So the degree here, let's just say that that's maybe a 2. Okay, let's not go too crazy and say, well, it could be raised to the 8th or the 10th or the 12th or the 20th or the 40th, because those are all even values. But let's be a little bit more conservative with this for now and just work with the square. Okay, so the last thing that we want to note here is, all right, it looks like I'm cutting through the x-intercept here. So we have our x-intercept, and our x-intercept is at point 1, 0. Okay, so in this case, we can translate this into the binomial x minus 1. And what I also want you to know, take a look at that image carefully. I was very deliberate in how I drew that line. Notice that you have a section of it that kind of is laying right across the x-axis. It's draped there. It's not slicing through really quick, so it's not just connecting through the dot and then going back up. It seems like it's kind of slithering up and resting on the x-axis, and then cutting through and going up. So because we are cutting through, we know that the degree of this polynomial is odd, but the fact that it's not a clean, so for example, just as an aside, if you have a point here, because the line isn't just quickly cutting through, we're actually seeing something where it's coming up, it's kind of resting, and then it's going up. That's going to tell you that the degree is going to be bigger than 1. Okay, you're going to have an odd degree that is bigger than 1. Again, we want to try to be conservative with this. So let's just say that it has a power of 3 in this case. Okay, so now we actually have all the pieces together, and we're ready to assemble them. So again, we'll go through here and we'll say, we'll call this function h of x. There's no particular reason why, I just felt like picking h. So we have a, we're going to figure that stretch or compression factor out later. We have our x-intercept, it's going to be x minus 1 raised to the 3rd power. I need to slow down. Then I also have my vertical asymptotes, which will reside in the denominator portion of this rational function. We have one at x plus 1, and then times x minus 2 squared. Okay. Here again, let's talk about this. The main issue that we have here is figuring out what a is. Well, think of this really quickly. We know that we have the horizontal asymptote y is equal to 2. And basically what I'm telling you is if I have a horizontal asymptote that is not resting on the x-axis, that is existing anywhere else, we know that the degree in the numerator matches the degree in the denominator. And again, please refer to your textbook on page 194 if you need to refresh yourself on those horizontal asymptote rules. So from here, we know that the degrees match. And take a look. So the degree in the numerator is a 3, and the degree in the denominator is a 1 plus a 2 or a 3. So that means that my compression or stretch factor is actually going to be that horizontal asymptote. So my final solution is going to be h of x is equal to 2 times x minus 1 cubed all over x plus 1 times x minus 2 squared. Please let me stress to you that I understand that some of it might seem like it's a little bit like magic, like, oh, the 2 is just the stretch or compression factor, and it's just because it's magic, or because I pulled it out of the air, or because I just want to be done with the problem and I want to put a number in there and just say I'm done. There is accuracy behind it. Okay, so the issue here is, if you think about it, and again, I've done this on the previous video for you, if we were to take this and kind of expand out the function, I'm going to kind of just focus on the Lie coefficients, because that's actually where we determine our horizontal asymptote. If we were to do x minus 1 cubed, if we did x minus 1 times x minus 1 times x minus 1, we would have an x cubed as our lead term, and then we would distribute the 2 to each of those terms, so then we would have that, that lead coefficient as 2. And again, if we were to multiply x minus 2 times x minus 2, that gives us a lead term of x squared, and then we're going to go ahead and distribute it with the x plus 1, and that's going to leave us with a lead term of x cubed, and then again some other terms or some other monomials after it. So if you take a look, and again stressing that if you don't see the coefficient then it's a 1, well, if we want to know what the horizontal asymptote is, again because the degrees match, we would take the ratio, and that would be 2 over 1, or 2. You use this technique because sometimes when you take a look at the graph that you're provided, there's no guarantee that the points that you're looking for are as clean cut as you would like. So for example, if you have a point that looks like it's going through the point, let's see here, say we had a point 0, 1/2. Well, in actuality, your eye is trying to bring you back to something that's familiar. But in reality, that point might actually be 0. I don't know, 0.574. So it's close. It looks like it's the y-intercept of 0, 1/2, but it's actually something a little bit further or a little bit larger than it. So again, the idea of working with the horizontal asymptote will help you arrive at the stretch or compression factor when you are building these rational functions. I hope that that helped. Before I go, again, what I have highlighted or boxed in pink is your final solution. The other stuff that I was talking about after that was just to reinforce why we are able to use the horizontal asymptote in order to arrive at what our stretch or compression factor is. All right? Thanks.